Good morning, students. Our next theorem is closed linear operator. So let T is a linear operator from dt into y. Here dt is the domain of T, which is the subset of the norm space X, and y is also a norm space. Then we are to prove that T is closed if and only if T has the following property. If Xn converges to X, where Xn is an element of domain of T, and image of Xn under T converging to Y, then X belongs to domain of T and image of X under T, that is Y. Now, because T is closed by definition if and only if its graph is closed, and if and only if graph is closed, if and only if its closure is equal to the graph itself. Now, graph is closed if and only if for every element Z of the form of ordered pair consisting of elements X and Y belonging to the closure of graph, this condition must imply that Z belongs to graph of T. It means Z belonging to closure of graph of T if and only if there exists a sequence consisting of the elements Zn of the form of ordered pairs X and Yn belonging to the graph of T such that the sequence Zn converges to Z. These Yn are of the form of T of Xn. So, Zn converges to Z, it means if and only if the ordered pair Xn, Txn, this converges to Xy. It means the sequence formed by the ordered pairs Xn, Txn that converges to the ordered pair Xy. Here, Xn belongs to domain of T, and this condition holds if and only if Xn converges to X and T of Xn converges to Y. Now, Z belongs to graph of T. By definition, Z belongs to graph of T if X belongs to X and Y is equal to T of X, and X belongs to domain of T. So, from the second equation, we can say that graph of T is closed if and only if Xn converges to X and T of Xn converges to Y, where Xn belongs to domain of T. And this implies X belongs to X and Tx is equal to Y, where X belongs to domain of T. Now, by the first equation, T is closed if and only if graph is closed. So, we can say that T is closed if and only if Xn converges to X and T of Xn converges to Y, implies that X belongs to X and image of X under T is Y, for Xn belonging to domain of T as well as X belonging to domain of T. So, this completes the proof of the theorem closed linear operator. Now, next there is a lemma based on closed operator. Let T is bounded linear operator from dt into y. Dt is domain of T, which is the subset of X. X and Y are the normed linear spaces. Then we are to prove that domain of T is closed subset of X, then T is closed. And if T is closed and Y is complete, then domain of T, which is contained in X, is closed. So, first of all, let us take domain of T, which is subset of X, that is closed. Suppose Xn is a sequence in the domain of T such that this sequence Xn converges to X and is such that T of Xn sequence that is also convergent. Now, let us take X belongs to closure of dt. Now, because domain of T is closed and therefore X belongs to dt closure implies that X belongs to domain of T. Now, because t is bounded linear operator, so we can say that t is continuous, and continuous operators always preserves convergence. So xn converges to x implies that image of xn under t converges to image of x under t. It means t of xn converges to t of x. And so by the above theorem, we can say that t is closed. Now, in the second part, we are given that t is closed and y is complete. We have to prove that domain of t that is closed. It means we have to show that domain of t closer is equal to domain of t. So let us take an arbitrary element x belonging to closure of dt. Now by definition of closure point, there exists a sequence xn in the domain of t such that the sequence xn converges to x. Now let us consider norm of txn minus txm. Now this can further be written as norm of image of xn minus xm under t. Now because t is bounded linear operator, so by definition of boundedness, this will further be less than or equal to norm of t into norm of xn minus xm. Now because the sequence xn is convergent sequence and therefore it is Cauchy sequence, and therefore this expression will approach to 0 as n and m approaches to infinity, and therefore from here we can say that norm of txn minus txm approaches to 0 as n and m approaches to infinity. So by definition we can say that the sequence txn that is Cauchy sequence in y, but y is complete space, and therefore the sequence txn that will be convergent in y. So the limit of txn is an element of y, and that element we have taken as y. Now because t is closed and therefore we can use the last theorem. So by using last theorem, x belongs to domain of t and y is equal to tx. So x belongs to dt closure implies that x belongs to domain of t. So this proves that domain of t is closed. So this completes the proof of the theorem. Now next we prove that the closedness does not imply boundedness of a linear operator. We will give an example to show that the closedness does not imply boundedness of linear operator. So let us take an example of the norm space, the space of all the real valued continuous functions defined on the closed interval 0, 1, and let us take t be an operator from dt into x given by t of x is equal to x dash, and dt is a subspace of functions x belonging to x which have continuous derivatives. Then t is not bounded but closed. T is not bounded because if we find t of x raised to the power n, from using this definition, this will be n into x raised to the power n minus 1. Now because n is arbitrary, so we can say that t is not bounded. Now we will show that t is closed. So let us take a sequence xn in domain of t such that the sequence xn converges to x and t of xn that also converges. Now by definition t of xn is xn dash, and let us take that converges to y. Now since the convergence in norm of this space is uniform convergence and therefore xn dash converges to y implies that integral 0 to t y tau d tau is equal to integral 0 to t limit of xn dash tau as n approaches to infinity. Now this limit can be taken outside of the integral, so this will become limit n approaches to infinity integral 0 to t xn dash tau d tau. From here, simplifying this integral, this will become limit n approaches to infinity x and tau between the limits 0 to t. So substituting the limits here, this will become the value of xn at t minus the value of xn at 0. Applying this limit, this will become limit of xn is x. So this will become xt minus x0. So we have obtained the value of xt from here, which is given by the value of x at 0 plus integral 0 to t y tau d tau. And therefore, we can say that x belongs to domain of t. And from here, the derivative of x is given by yt. And we have obtained tx is equal to x dash, which is y. So by previous theorem, we can say that t is closed. So we have shown that closedness does not implies boundedness of the operator. This operator is closed here, but that is not bounded.